Hi to all. Today's topic is AC voltage applied to a series LCR circuit. In AC chapter, in alternating current chapter, previously we discussed AC voltage applied to alone resistor, next inductor alone, next capacitor alone we discussed. Now we are going to discuss if inductor, capacitor, resistor 3 are connected in the series and their combination connected to a AC source, that voltage is V equal to V naught sin omega t. Then I am going to explain how the current will changes and how to calculate the total resistance of the circuit and when the current will be maximum, and such all concepts I am going to explain related to this. Our topic is now AC voltage, AC source is applied to LCR series circuit. In this, what is there? Source voltage does not changes. Either AC applied to resistor or inductor or capacitor, whatever it may be, the source voltage always we will take as V is equal to V naught sin omega t, because voltage is alternating voltage, it varies with the time. And in this, the terms if we will discuss, V naught is the peak value of voltage and omega is the angular frequency of AC and I naught is the peak value of current or amplitude of current. And now if we write the equation according to the Kirchhoff law, then how we will get? Let us see here. From this equation, the voltage across this equal to voltage across this, right? Then according to Kirchhoff law, we can write, or from figure we write, okay, from figure we write one thing, that is the voltage of AC source voltage is equal to, we write as VL plus voltage across inductance plus voltage across capacitance plus voltage across resistance, right? But what is the voltage across inductance? Voltage across inductance we write like this, okay, just I will explain. I am searching for the duster. Right. Voltage across, total voltage equal to voltage across inductance plus voltage across capacitance plus voltage across resistance. But we have to take in the vector form. Remember this. This is vector form. We have to take as rotating vectors. We have to consider angles also, right? And now V is equal to, we have V naught sin omega t. This we write as voltage across inductance we know as L di by dt plus voltage across capacitance we write as Q by C, voltage across resistance we write as IR. This is the equation for LCR circuit. And everywhere we are finding the instantaneous current equation, right? Here if you solve this equation, it is a differential equation. If we solve this, then instantaneous current we will get like this. I is equal to I naught sin omega t plus or minus phi you will get, okay, plus or minus phi. Either you may get plus or minus, okay. What is phi at here, right? What is phi at here? Its derivation is not there in our syllabus, right? And in higher education you will learn. This is equation 1 and 2. From equation 1 and 2, what is the phase difference between the current and voltage, right, in LCR circuit? Phase difference between current and voltage or EMF in LCR circuit, in LCR series circuit, right? Then what is the phase difference? Yes, you know, these subtract these two, right? You will get the phase difference as phi. In this we are getting the phase difference as phi. What phase difference gives? Phase difference gives the current angle between the voltage and current. It will give the angle between the voltage and current, okay, right? That is angle between voltage and current In phasor diagram, you know already phasor diagram? Phasor diagram is phi, you remember it. Phase difference gives the angle between the current and voltage. In this chapter, alternating current, we will take the current and voltage as vectors. Then if you indicate the diagram in which the alternating current and voltage are indicated by rotating vectors in anti-clockwise, that is called as phasor diagram. Current phasor, voltage phasor, we are taking the current as vector, that is called as phasor, current phasor or voltage phasor. Okay, and note every point. Then I will rub and I will continue. Okay, now let us draw the phasor diagram in this. Okay, then for the phasor diagram, first we know to draw the phasor diagram, what we have to do, we have to indicate the current and voltage in the circuit as rotating vectors. For example, if only inductor is there, right, what is the situation, how the phasor diagram will be there? Only resistor is there, then how the phasor diagram is there? If only resistor is there, for example, this is the resistor, look at here, and this is AC through resistor. In case of resistor, AC applied to resistor, AC applied to resistor. If AC applied to resistor, this is the diagram, right? That is, voltage across resistance is right side and the current also right side. Here the phase difference is 0 in this case, no phase difference. This is the first diagram. If we have only inductor, right, second case is that inductor. If we have only inductor, the diagram will be like this there. This is the current and this is the voltage across inductance. Right, voltage across inductance, this is 90 degree. And if we have only capacitor, the diagram will be like this there. This is the current and this is the voltage across capacitance, right? In all these cases, we are indicating, right, we are indicating the current and voltage as rotating vectors in anti-clockwise direction, like this, like this, like this, right? And this is for resistor, this is for inductor, and that is for the capacitor. Individually phasor diagrams we discussed, and we have to combine these all things. In LCR circuit, inductor is, resistor is there, inductor is there, capacitor is there, right? We have to combine these figures, combine above figures. When we combine above figures, then how you will get? What you will get? Right? If we have only resistor, right, we will get like this. We can draw to a side. This is the resistance, voltage across resistance, and the current. Both are in phase. And if you take only inductor, right, this is the diagram, this is the voltage across inductor, right? Current and voltage, this is the combination, current and voltage, second diagram. And the first diagram is current and voltage, same direction, right? And the third diagram is, this is the voltage across capacitance, right? And here, this is the situation, current and voltage. This is I and this is VC. This is third diagram. This is the combination of three diagrams. Combination of three diagrams. If we combine these D diagrams, then how you will get? Okay, and the same diagram I will draw to this side. First again I will repeat. the current and voltage across resistance in the same direction. This is the voltage across resistance and the current. And the voltage across inductance is upward, right? This is voltage across inductance. And this is voltage across capacitance. You see here. This is IVC, this is IVL, and this is IVR. IVR, IVL, IVC. And if we do like this, for example, I am considering that if VL is greater than VC, if we consider, then the net of these two we have to subtract the voltages because they are in opposite direction, right? Then we will get like this. This is VL minus VC, okay? And this side current will be there. And this side voltage across resistance also there. Now VL VC are in opposite direction, that's why we subtracted VL minus VC, their net voltage. And here VL minus VC this side and VR this side, their net is this side. This is the net voltage V. Okay, the angle between the net voltage and the current we know in LCR circuit is phi. Then if you draw the phasor diagram it here, okay, right, if you draw like this, if you draw a rectangle at here, if you draw a rectangle like this, you will get. And now this is VL minus VC means this is also VL minus VC. And this is VR, this length is VR, right? This length is VR. And this is also VR, right? And this is the net voltage V. This is the net voltage V. Okay? Right. From the figure what we can write? From figure, net voltage we write as V is equal to, right? It's a Pythagoras principle we can apply. This is how it is there. You see here, you remember this is V and this is VR and this is VL minus VC, right? This angle is phi. Pythagoras principle you can apply, or the vector law, anything you can apply. Then you will get VR square plus VL minus VC whole square, right? This is equation. Previously we consider the equation phi, up to phi we consider. Next continuation I am going to give. This is 6, right? I am taking the V as the total voltage. VR if I naught is the peak value of current. If I naught is the peak value of current. I am taking all the peak values. Then I want the peak value of voltage across resistance. Peak value. Peak matlab maximum value. Peak value of voltage across resistor, right? Across resistor. What you will get? We will take it as VR. There is a current into resistance, right? Peak value of current into resistance. This is equation. And the next peak value of voltage across inductor I want. This is across resistor, right? Peak value of voltage across resistor. Across resistor what you got? That is VR is equal to V naught. Sorry, voltage means current into resistance, right? Peak value of voltage equal to peak value of current into resistance. And across inductor, right? Across inductor, what we write? Voltage across inductance equal to peak value of current into resistance of inductor. Resistance of inductor is XL. Across capacitor, right? Across capacitor I want the peak value of voltage. that is Vc. It is the peak value of current into peak resistance of the capacitor, that is I naught into Xc. This all we can substitute in this equation. Okay, right. If you substitute, this is the peak value of voltage, then we will get the peak value of current formula. When these all we write as peak values, then net, this is also we will get the peak value of net voltage. Then V is equal, we will get as V naught. This is the peak value of voltage, net voltage, total voltage, right? When you substitute all peak values VR, VL, VC, then V also you will get V naught. This you all substitute, right? We substitute VR, comma VL, comma VC and V are substituted in equation 6. Then what you will get? Now let us substitute all the things. V is the V naught is equal to under root of, you will get as a VR is I naught R whole square plus VL minus VC. V naught is I naught XL minus I naught XC whole square, we write. Now we have to simplify more. You take the screenshot and note it, then I will continue after the rubbing. Okay, now I am going to rub it. Let us simplify that. V naught is equal, we will get as right side. You see this equation. I naught square R square plus I naught is common at here. I naught square into I naught square, I naught is common, whole square will be there. Remaining is XL minus XC whole square. XL minus XC whole square, right? Okay. Here I naught square is common. Then V naught is equal, we will get as I naught square, if you will common, I naught square into R square plus XL minus XC whole square we will get. This I naught square will become like this. I naught square will root cancel, then we will get V naught is equal to I naught into under root of R square plus XL minus XC whole square. From this, if you write the peak value of current equation, right, I naught is equal, we will get as V naught by under root of this I naught equation I want, R square plus XL minus XC whole square. This is a very important equation. This is equation 7. In this you see, this is the peak value of current equal peak value of voltage by this one. And then we know already, we know peak value of voltage formula. What you know peak value of voltage formula? That we know as I naught equal to V naught by Z, right? V naught by Z. This is equation 8. What is Z here? Total current. Current equal to voltage by resistance. Resistance of total circuit we have to take, because this is a total current in the circuit. Total voltage by total resistance. Total resistance in AC circuit is called as impedance. Z is called as impedance. Impedance means total resistance of circuit. Resistance of circuit for the flow of AC. For the flow of AC. Okay, right. When you compare equation 1 and 2, sorry, equation 7 and 8, compare equation 7 and equation 8, then we will get Z is equal to right? Z is equal, we will get as under root of r square plus xl minus xc whole square. This is very important equation. This is the impedance equation. What is Z here? Impedance in the circuit. What is impedance? Already you know. There is a total resistance of the circuit. We cannot add the resistances R, XL, XC. Resistor resistance, resistor resistance is R, inductor resistance is XL, capacitor resistance is XC. These are all in series, but we cannot add them because we have to take like vectors. In the vector notation, the effective resistance is the Z is equal to root R square plus XL minus XC whole square. In DC circuit we can add the resistances directly, but in AC circuit we have to consider the phase differences also. That's why we will get the diagram, we will get the value like this. Okay, now I am going to continue. Listen very carefully, this is the most important topic and it will come for the 5 marks. Next, I am going to continue. Impedance triangle. There is an impedance triangle is there. What is this impedance triangle? Right? You see. We know already the diagram like this there. This is a net voltage. This side voltage across resistance. This side VL minus VC, right? This already we know. This is VL minus VC. And here this angle between the net voltage and current. This is also current also, right? Is the phase difference. This equation we draw like this diagram. Instead of taking this voltage across resistance, we will take the resistance. Instead of taking the voltage across inductance and capacitance, we will take VL minus VC as XL minus XC. Resistances we will take. Here total voltage, instead of total voltage, we take the total resistance. The total resistance is called as Z. And this is angle is phi. Phi is the phase difference. This is to be impedance triangle. From the impedance triangle also we write direct impedance as, right? We write direct impedance equation. Impedance as, what do we write impedance? Impedance Z is equal from the triangle under root of R square plus XL minus XC whole square. We write directly also. Impedance means the total resistance in the circuit. Total resistance in the circuit. I want the phase difference between the current and voltage in LCR circuit. Phase difference between current and voltage in LCR circuit. In LCR circuit, what you will get? Sir. Okay, see here the phase difference between the current and voltage in LCR circuit I want to derive the formula for the phase difference. For that, from figure, from impedance triangle, right? It is said to be impedance triangle. From impedance triangle we write like this, right? What we write, tell me? From the impedance triangle you can write the tan phi is equal opposite side by adjacent side. Opposite side is VL minus VC by VR. We have to take the voltages only. And this is VL is nothing but we can write maximum voltage across inductance. Here it is I naught XL minus I naught into voltage across capacitance, current into resistance of the capacitance. Resistance of the capacitance is called as XC. Resistance of the inductance is called as XL. Voltage across inductance equal to current into resistance of the inductance. Voltage across capacitance equal to current into resistance of the capacitance. Voltage across resistance equal to current into resistance of the resistor, right? Then we will get the tan phi formula as XL minus XC by R. Okay, this is the formula. Now we will take this as equation 1. Equation 9. Okay, from this also directly we can write tan phi equal to XL minus XC by R, opposite side by adjacent side. Now I am going to continue here. In the left side some cases I will explain, right? Listen very carefully. That is the case 1. The case 1 is that if XL is greater than XC, then what is the condition? If XL greater than XC, that is the inductive reactance is greater than the capacitive reactance. At that moment, this is the net voltage and the current. The phase difference phi will become the positive, right? You see here, XL greater than XC means the phi is the positive. And in this, inductor effect is more. Then the LCR circuit is said to be inductive circuit. Then the circuit is called as inductive circuit. Circuit is called as inductive circuit. Why it is inductive? Because effect of inductor is more. In this case, when you will get the phi is positive, at instantaneous current we write like this, right? Instantaneous current equation, right? In LCR circuit, instantaneous current formula is I is equal to, we write as I naught sin omega t minus phi we have to write, okay? This is equation 10. And here this is minus phi. Why we got the minus phi? Okay, here the phi is positive. Here I may be I naught sin omega t minus phi. In inductor circuit, in AC through inductor circuit, right? AC through inductor circuit, omega t minus 90, only inductor if it is there. Here minus phi, because the remaining also there, that's why we write minus phi. And here we write in inductor circuit, here we write the current lags voltage by phi, okay? Now in LCR circuit, in inductive LCR circuit, let us see here case 2. Let us see, if XL less than XC, then the phi is negative, right? Phi is negative. Then circuit is said to be capacitive circuit basis, because the effect of capacitor is more, right? In this case, instantaneous current equation we write like this. Instantaneous current equation we write as I is equal to I naught sin omega t plus phi we write. Okay, it is no need to give the equation number. And in this we say that the current angle is more than the voltage angle. The voltage angle is always fixed. V is equal to V naught sin omega t. That's why we write the current leads. Okay, current leads voltage by an angle phi. Okay, right. We can also say that voltage lags current by phi. Case 3, let us see. Case 3, right? The case 3 is that if XL is equal to XC, then what happens? The phase difference becomes 0, right? Phase difference becomes 0 from the equation 9. XL is equal to XC we write. Then phase difference is 0. Okay? When the phase difference is 0, then the circuit is called as a resistive circuit, right? Circuit, CKT we write circuit. Resistive circuit we say, resistive. Okay? In the resistive circuit, the phase difference is 0 means, then the current equation we write as I equal to I naught sin omega t plus or minus phi, but the phi is 0, here we write like this. Then the voltage equation also same. Then voltage angle is omega t equal to V naught sin omega t. Current angle also equal sin omega t. That means same angle. Then we say that in resistive circuit, only resistor, right? Then the current is in phase with voltage. Phase difference is 0. Okay, this is the cases when the circuit is said to be inductive, when the circuit is said to be capacitive, when the circuit is said to be resistive. That conditions they may ask in the exam. If inductor effect is more, then inductive circuit. If capacitor effect is more, if Xc is more than XL, then it is said to be capacitive. If both are equal, then it is said to be resistive circuit. Okay, right. And the next important point I am going to explain, that is the resonant circuit. What is the condition for the resonance in the LCR circuit? I am going to derive the formula for the resonant frequency in LCR circuit. Resonant frequency in LCR circuit. Okay, resonant frequency in LCR circuit I am going to derive. What is resonance? This LCR has its own frequency. LCR circuit has, when the current passes through it, it will oscillate. It has certain frequency. Okay, and LCR has certain frequency and the AC source has certain frequency. If the frequency of AC source match with the frequency of LCR series circuit, then the maximum current passes through it. Then we say that it is a resonance. Okay, now in the resonance means, actually in SHM topic, simple harmonic motion, in the first year we discussed the resonance. That in that what we discussed, then for example this is a swing. If it is oscillating like this, it has its own frequency, that is the natural frequency, and somebody is pulling and or the pushing, then that pulling and pushing frequency is okay. If that is the applied frequency, it is the natural frequency. If the natural frequency of the swing is equal to the frequency of the force or the applied frequency, then the swing oscillates with large amplitude, right? That is called as resonance. The resonance means the frequency match should occur. Now the peak value of current in LCR circuit, we know the peak value of current formula. Yes, what is the peak value of current formula? The peak value of current formula is I naught is equal to, we know, V naught by Z. Z is under root of R square plus XL minus XC whole square. Now this is the current equation that we know already, and now I want, when the current will become maximum, then in order to get the maximum value of current, this should be minimum. When it will be minimum, this denominator, because the current peak value of current inversely proportional to this, the impedance should be minimum. This we can also write as V naught by Z, right? Okay, and Z, when it will be minimum, if XL is equal to XC, then this will become 0, then this total term will be decreases, then this will be increases. That means if XL is equal to XC, then impedance become minimum. Impedance become minimum because this total term become 0. And when impedance becomes minimum, then the current become maximum. Current become maximum. This we can take as I naught max. Then what is the current maximum? Then the circuit is said to be resonant circuit. Then the circuit is said to be in resonance. Then the circuit is said to be in resonance. What is the condition for the resonance? Condition for resonance is that XL should be equal to XC. XL should be equal to XC, and that is impedance should be minimum. Okay, right. If XL is equal to XC, we write XL is the L omega, XC is the 1 by C omega. XL is the inductive reactance, resistance offered by the inductor for the flow of AC. XC is the capacitive reactance, resistance offered by the capacitor for the flow of AC. For AC, resistance of the capacitor is capacitive reactance. For the AC, resistance of the inductor is called as inductive reactance. Then when we do like this we take to left side, omega taken to left side, omega square is equal to 1 by LC. From this we write the omega formula, right? Omega is 1 by root LC. 1 by root LC. This is the formula for the resonant frequency. Resonant frequency. Okay, and this we can take as equation. I think this is 10. Okay, and this is the omega. Here it is resonant frequency, right? Resonant frequency, that is the angular frequency in LCR circuit. In LCR circuit, this is the resonant angular frequency. If you want the linear frequency, right, general frequency, then omega we can replace with 2 pi nu. Okay, this is the resonant frequency. If XL is equal to XC, then impedance become minimum and current become maximum, right? Current become maximum. That is called as resonance, right? At the resonance, we got the frequency that is omega equal to 1 by root LC. And you take the screenshot and note it, and I will continue after the rubbing from the left side. Now I am going to rub it. Here we got the angular frequency. Okay, omega is the angular frequency, right? Angular frequency. Angular frequency. Angular frequency. But omega we write as 2 pi nu, right? You know, omega is the 2 pi nu. We write here, where nu is the general frequency, right? From equation 10 we write like this. From equation 10, that is 2 pi nu is equal to, we write as 1 by root LC. We write nu as 1 by 2 pi root LC. This is the general frequency, right? This is equation 11. This is the nu is the frequency of LCR circuit. Okay, what is which frequency it is? Resonating frequency. Resonating frequency, right? Resonating frequency. Resonating frequency or resonant frequency. By changing the value of L and C, we can change the resonant frequency of LCR circuit. And if you draw the, in this at resonance, I want the peak value of current. At resonance, what is the peak value of current? Peak value of current at resonance. Do you know what is the value? That is I naught is equal to, that is I naught max, right? That is equal to, we write here XL is equal to XC, then we will get the current as I naught max. That is V naught by only R. That means the peak value of current depends upon the resistance. If the R is less, then the peak value of current will become more, right? Okay, because they are inversely proportional. This is equation 11. At resonance, the peak value of current. In the normal, peak value of current formula this one, but at resonance, XL is equal to XC condition if you write, then you will get this equation. And now I want to draw the graph between the peak value of current and frequency. Okay, right? And that is I naught max, I naught versus omega graph or the frequency graph. Then how you will get? Let us see here. I will take this one, the graph I will draw by taking omega on x-axis and the current, peak value of current on y-axis. We will get the graph like this. Or only two we write, only two we draw. You see here, right? This is the resonant frequency, right? At that the current become maximum, and this is I01 and this is I02. Okay, and on the y-axis what you are taking? I0, peak value of current. And here this one has the resistance R1, we will take, this one has the resistance R2. In this, the peak value of current for the second one is more, right? And that here we write R1 R1 greater than R2, that's while I01 is less than I02. Okay, this one has more resistance, this curve, that's why its peak value of current is less. This one has less resistance, that's why its peak value of current is more. If you want the more current, you should keep the resistance at less value. If you want less current, then you have to keep the resistance more value. This is the simple diagram. At a particular frequency, this frequency is on x-axis. At a particular frequency, that is omega r, it is a resonant frequency. A resonant frequency we can denote with omega suffix r, or simply omega also we can denote. Okay, then there is no problem. And resonant frequency, if you want to denote like resonant frequency, right, the frequency is called as a resonant frequency, you can write omega r also, there no problem. Omega suffix r, resonant frequency, omega suffix r, omega suffix r. Okay, and this is the 2 pi nu suffix r, that means resonant frequency, that's all, resonant frequency. Okay, right, and take the screenshot and note it. One point here it is missing. Look at here. When xl is equal to xc, z is equal to minimum. Okay, xl is equal to xc, this value become minimum. Then what is the impedance at the resonance? What happens to the z? Z is equal to r, because this is totally z. But when this is 0, and you will get under root r square plus xl minus xc is the xl minus xl whole square. Then this will become 0, then z is equal, we will get as r, right? At resonance, the impedance is equal to resistance. At resonance, xl is equal to xc, this term will become 0, then z is equal to root r square, that means z is equal to r at the resonance. Okay, let us go for one problem based on LCR circuit. Look at here, this is the inductor has inductance 5 Henry and the capacitance is 80 microfarad, that is 80 into 10 to the power of minus 6 farads, and the resistance is the 40 ohm. It is connected to a source of voltage. RMS voltage is AC voltage they gave, that is 240, that means it is RMS voltage. First they are asking to find the angular frequency, omega is equal to what? At the resonance, omega r. And the second question is that the current at the resonance. The current at the resonance is what? The third question is that RMS potential across the capacitance. Potential across the capacitance is what? These are the questions. Let us see here, this is the LCR series circuit. LCR series circuit, this is the inductor and this is the capacitor, this is the resistor. These three are connected in series like this to AC source. This is the AC source, right? This AC source voltage is V, and through this at any instant the current we can take as I, right? Then the voltage across capacitance is VC, and the voltage across resistance is VR, and the voltage across inductance is VL. Now let us see the first question, the resonating frequency. What is the formula for the resonating frequency? Omega r is equal to 1 by root LC. Right, now you substitute all values in this. 1 by root L, inductance is what? 5 Henry. Right, into C is 8 into 10 to the power of minus 6. Now we have to simplify this. For that, the resonant frequency is 1 by root, this is 5 into 80, 400, into this is 10 to the power of minus 3 whole square. This will become like this, 1 by root 400 is 1 by 20 into 10 to the power of minus 3. This will become 1000 by 20, 0 0 cancelled, and the resonating frequency we will get as 250 ja, that means the 50 radian per second. The second question is that they are asking to find the peak value of current at resonance. Okay, at resonance current, general current formula is I naught is equal to V naught by under root of R square plus XL minus XC whole square. But at resonance, what happens? At resonance, XL is equal to XC, right? You know that one, XL is equal to XC. That means these two will cancel. XC, this is XL. XL, this is XL, and this is XC, right? But these two are equal, they will cancel with each other. Then I naught max with formula we will get as V naught by, you write XL, XC cancel, then you will get V naught by R. What is the peak value of voltage? Peak value of voltage, do you know? Right? We know RMS. Then we want the peak value of voltage. We have formula for the VRMS. RMS voltage is equal to V naught by root 2. Then based on this, we write V naught is equal to root 2 VRMS by using that formula. This root 2 is for only root 2. For the VRMS, root 2 is not there. Root is not there. Right? Now substitute all values in this. Peak value of current. They are asking the current at resonance frequency. Current means we have to RMS current we can find out. It is very easy to find out the RMS current, right? At the resonance, the current is directly we write. No need of these all things. Yes, at resonance formula is what? Current is what? At resonance, the peak value of current formula is peak value of voltage by resistance. Because here we know at resonance XL is equal to XC. That's why you will get this formula. If you want to write the RMS current, right? And you write VRMS by R. Now VRMS we substitute here. VRMS is what? 240. Right? By resistance is 40. 0, 0 cancel. 4, 6, then 6 amperes is the current. The third question is that they are asking to find the potential drop across the capacitance. Across the capacitance, potential drop is current into resistance of the capacitance we have to write. Then this is the current is IRMS. XC we write as 1 by C omega. XC we write as 1 by C omega. Now substitute all values. What is IRMS? IRMS is at resonance 6 amperes, right? And C omega, what is the C value? 8 into 10 to the power of minus 6 into omega value is what? Omega value is 50. Now we have to simplify it. Then we will get the answer. That is voltage across capacitance is, right, 6 by 8 into 5, 40 into 10 to the power of minus 4 we will get. This is nothing but 3 by 2. This will become 10 to the power of minus 3. It will goes to numerator. 10 to the power of plus 3. Right. Then we will get the 3000 by 2. We will get the 1500 volts. This is answer. Right. Okay. Thank you for watching my lectures. Till now, if you not subscribe my channel, subscribe. If you have any doubts, you can comment. Thank you.